Hello, everyone, and thank you for joining us today. My name is Parrish, and I will be your host for this webinar on the plasmid technologies for pH control and nutrient recycling, sponsored by NASA's Technology Transfer Program. In my job as a Senior Technology Transfer Specialist, I support this program and work with NASA scientists who have developed new technologies that may have applications outside of the aerospace industry. We patent these inventions and market them to industry through our website, which I'll show you later, as well as through efforts like today's webinar. Our presenter today is Dr. Kenneth Engeling. I'd like to give you some background on our presenter. Dr. Kenneth Engeling received his PhD in nuclear engineering and radiological sciences from the University of Michigan in Ann Arbor in 2019, with a focus in plasma physics. Since 2020, he has performed research at Kennedy Space Center and focuses within plasma physics and plasma chemistry. Some of his work includes waste gasification, toxic gas abatement, lunar mining, fuel production, and advanced sensing techniques. Prior to joining NASA, he worked for the Air Force Research Laboratories as a contractor on high-power microwave systems. He is an innovator on 23 NASA New Technology reports. Following today's technical presentation, I'll be giving a short presentation on how NASA licenses technologies to outside organizations. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the chat box and we will answer them during the Q&A session at the end. At this point, I'm going to turn it over to Dr. Engeling.
Good afternoon, everybody. I appreciate the opportunity to discuss with you today from Kennedy Space Center on some of the work that we've done. I'm going to go ahead and share my screen here. So thank you for the introduction, Lou, and welcome everybody. So I'll be talking about the plasma processing of water, nettable biomass ash leaching as part of our NASA Tech Transfer Program here at Kennedy Space Center. So what I'm really going to introduce today is just an introduction to the topic. Not everybody here may be familiar with the plasma, so I'll give some high-level information on what a plasma is, so you have a better understanding of the process presented here, as well as other applications that plasma may be able to aid. Then I'll break down into our work here of the plasma processing of water, the terrestrial agricultural applications, including the nettable biomass, some of the possibilities that I see in it, as well as commercialization and future development of the work presented here, as well as in the industry in general. So a little bit of background of myself in the lab. I work in the applied chemistry lab here at Kennedy Space Center. We do gas sensing technology. We work on astronaut waste management, logistics reduction, hypergolic fuels compatibility detection, as well as resource remediation and reutilization. As Lou mentioned, I'm a nuclear engineer focused in plasma physics. I'm still getting started in my career, but this work, even though I'm the one presenting today, I'd really like to highlight that the work is a team effort. We have molecular biologists, analytical chemists, chemical engineers, aerospace engineers, and really, a lot of the work's done with our intern team. So even though I focus in plasma chemistry, we have a well-rounded group performing the work. So for folks that are kind of new to the topic and new to what plasma is, just some everyday occurrences of plasma, right? Everybody thinks of the sun, which is shown on the right image, or the northern lights, Aurora Borealis, which is in the middle image here. But think of your microwave ovens. They use a plasma in order to generate the microfrequency waves that heat your food. For those of us that are older, you had the old cathode ray tube televisions. When you walk across the carpet in the winter and touch a doorknob, that static shock is a form of plasma. Or you can get to science fiction, right? Star Wars lightsabers, you have plasma weapons, things like that. So it's really pervasive in everyday life. And before I got into understanding what a plasma is, I didn't realize how many everyday occurrences that there were. And the advantages of using plasma, although this is we look at it for space-based applications, so electrical power, but there's a wide range of things you can do with the plasma. Our group in particular focuses on low temperature plasmas. But overall, the advantage is you have a modifiable temperature range. So on the image on the right, you can see you can get hot like the solar core, confinement fusion, magnetic fusion, or you can have cold plasmas, aurora borealis, fire, your neon signs. And a lot of our work really focuses in this, yellow outlined region, which is, for those in the plasma physics field, definitely recognize this image. So what we've done, a lot of it is demonstrated on a laboratory scale. There's some scalable technology out there, and for space, we want to limit or lower the use of consumables, right? We have to use everything with us. Terrestrially, it's more of an on-site, on-demand point of use production. Disadvantages that are typically associated with plasma systems are high electrical costs. They're not economic, but in the last decade, the community at large has made great strides into economic uses of plasma, and that it's also kind of a newer field, right? As electronics advance, our detection advances, a lot of this is still cutting edge research and application. So there's still a lot of room of improvement on the technologies I'm presenting here and across the field in general. So even though if you're in the plasma field, you get some kickback, a lot of people consider it the fourth state of matter. So you have a gas, solid, liquid, but if you heat up a gas or electrically ionize it, it becomes a plasma. So it consists of like a soup of ions, so positively charged particles, electrons negatively charged, and then just neutral. So it kind of a soup of this charged particles that you can move with electric and magnetic fields, and you can have hot and cold variations of it. And we in particular use it to form chemistry. On the right-hand side is a plasma reactor. So I was plasma treating soybeans in my graduate school days, and you can kind of see the glow discharges in between the dark shapes, which are soybeans, to try and enhance germination and growth. Just kind of an example of a cool plasma discharge. But for this topic in particular, we kind of focus on the plasma processing of water. So when you generate a plasma, you can kind of see it here at the bottom of the image, the purple kind of lightning bolt looking streaks. I have a video on the next page I'll show. But when you do that with an air plasma especially, you generate all these reactive species. So based on how you tailor your plasma supply, so your voltage, your frequency, duty cycle, or alternating current, direct current, radio frequency, you change the production rates of various species in here. So you can kind of tailor your plasma parameters to try and produce more hydrogen peroxide, which is this guy here, or produce more nitrogen dioxide, which becomes nitrate, NO2, which becomes nitrate in water, which is a plant usable form of nitrogen. All right, so you can tailor the plasma, the flow. So there's a lot of tunable knobs in order to do this. And that was one thing we explored here at Kennedy Space Center. So let me make sure the volume's off. Yeah, it's a high pitch, so it's annoying. But what you can see here is gas flow in bubbles in through a tube, and you can see the plasma forming. And all I'm doing right now is just changing the gas flow rate into the discharge. So it's changing the intensity of the plasma formation. It's becoming more conductive. So it changes our production rate, and you can see it goes out when I stop the gas flow. And the reason why is it's easier to generate a plasma in gas than it is to rip apart water molecules. So this is just a video demonstration. So previously, and what's reported is we made up to 200 parts per million of nitrate in 15 minutes. We were using a DC plasma jet. So it's a DC plasma jet, it's what's shown here. And 300 milliliters of DI water and 5 liters air. This isn't a very high production rate, but this was a proof of concept. But currently, we're able to produce 600 parts per million in 5 minutes at a fraction of the power, and we increase our flow rate using an arc discharge. So we've actually changed our setup completely from this plasma jet setup, and we've actually even observed up to 17,000 parts per million in water. So from an agriculture standpoint, 17,000 parts per million is way high. But what you can do is dilute it down to the application necessary. So for an example or reference, Hoagland's solution, which is kind of the standard for cutting fertilizer solutions for controlled environment testing, has around 210 parts per million of usable nitrogen. And we're able to generate 600 parts per million in 5 minutes using 100 watts of power and 15 liters per minute of air. Just comparable numbers for later. So this is just another example of a plasma jet in water a little bit. So you can see our 300 milliliters discharge in water and some gas flow formation. But once again, this was our previous setup, and we've improved upon it to get the higher numbers. So this is the focus on the plasma treatment of water, in particular for nitrate production in the form of nitric acid, so plant usable nitrogen. Well, that's great, except when you put nitrogen in water, it acidifies the water, and plants don't really like acidic water. So I want you to keep that in mind as I move forward, because when you harvest a plant, say a tomato plant, you have roots, stems, and leaves that you can't eat. You eat the tomato, it's delicious, but you can't eat the rest of the plant. So what do? Well, in space, we don't really have the time to have organic composter materials. So we want to try and break up the plant cell walls, cell membranes, and pull those nutrients out. So we had a little DC arc discharge. You can tell it's a modified spark plug here, to make a little plasma torch to plasma treat the inedible biomass. So those twigs, roots, stem, leaves, we ground it and pressed it into a pellet. Then we treated it with either an air plasma or a nitrogen plasma. And the reason why we change the gas is you change the chemistry that happens. And that's very pronounced here on the right-hand side. Your air plasma is much like a campfire. You can see the discoloration. You got a little bit of color, green here, some reddish brown, some gray. So much like your campfire ash. But if you use a nitrogen plasma, essentially strip all the oxygen from the processing that's not located in the plant itself, um, you can see it is much more representative of a biochar or a commercial ash. So that biochar, it is comparable to commercial biochar, and it can be used as a filter, or you can mix it in as a soil additive, as this biochar is a plant usable form of the nutrients. So the key deliverable of this project, is to recover the plant nutrients that the astronauts can't consume, to reuse in a closed loop crop cycle, right? We can't just go to the nearest store and get more fertilizer. Whatever we have up there is what we have without a resupply shipment. So what we did is mix the two. If you get acidic water and no nutrients plus a bunch of nutrients, you balance it, and you can try and grow plants with a closed loop cycle. So we did 2 microgreen growths. This was a cherry bell radish over the course of 9 days. We still did our direct current, so DC, air plasma, and deionized water, so ultra pure water, try and remove any of the variations in tap water that you may have. We treated it for 15 minutes and had a pH of 3. So this top graph here in section A, you have the Hoagland solution, which is the gold standard of fertilizer. It was cut to 1/4 strength or 1/8 strength. I don't remember off the top of my head. We have our deionized water, so water with no nutrients, and then plasma activated water by itself that has a pH of around 3. So surprisingly to the team, we did not expect the acidity of this water to even germinate the plants, but we were able to germinate. But when comparing the 3 to each other, you can see the Hoagland's microgreens 9-day growth looks healthy, it's green, it's beginning to flourish, whereas the DI and the activated water at the pH of 3 look very stressed, stricken. I'm sure if we let it grow longer, both of these would be not very good outcomes. So the plant would probably wilt and die. So then we did a second set, right? We had the recovered inedible biomass from the plasma processing, and then we had the added nitrogen from the plasma activated water. So once again, on the left, we have the Hoagland solution, so the ideal fertilizer, and then we have a pH of around 7. So we took the pH of 3, added some of this processed pellet to it to add nutrients, but also it brings the pH up as its basic and makeup. And I brought it to a pH of 7, and then another one to a pH of 9. So you can see, especially top to bottom here, the plasma activated water plus some of the nutrients from the pellets are more favorable. So you have a healthier looking plant in each of these cases with the plasma activated water plus the processed pellet additive, and then the non-nutrient DI water, as well as the plasma activated water alone with the low pH. And just for comparison, at Kennedy and on the space station, we use a slow release fertilizer pellet from Florican that releases around 25 parts per million of usable nitrogen per day. So that's kind of representative of what we can make at a low time. So we are high on the nitrogen content, but we can tailor our plasma discharge in order to balance the pH, balance the nitrogen content in order to achieve whatever the plant desired nutrient levels are. So when looking at a harvested mass versus dry mass comparison, the blue column or far left is our Hoagland's. So it's our ideal situation. And you can have our deionized water, our acidic plasma water, and then the two pellet plasma water additives. So when the most favorable was a plasma water with a pH of around 7, so 6.7, and the pellet additive in order to try and provide some of those missing nutrients that are used in just DI water. So although the dry mass is comparable, one thing that we still needed to do, and I'll highlight this later, is it's great that you can have the plant grow, germinate, and grow comparably from a dry mass perspective, but what's the nutrient content? What's the nutrient analysis? So there's still some work to be added there. So kind of looking at the two systems, you have the plasma activated water. There's multiple ways of implementing it, but say on a hydroponic or irrigation system, you could implement it there. So if there's a water reservoir or a holding tank, you can slowly add nitrogen content. Imagine powering this with solar to the water reservoir, or if there's an irrigation system, you can have it in line with the irrigation system as it's watering the field to supply basically controlled on-demand addition of plant usable nitrogen. Leafy greens and like your lettuces at various points in the growth cycle prefer a higher nitrogen content. And this is one way of doing it, especially if you get to crop circles in remote locations where, for instance, say the uh, high west New Mexican desert, they will truck in fertilizer twice a year and just flood the field with your nitrogen-based fertilizer that has a small amount of sulfur compound. But then you have a lot of agricultural runoff because the plants are at different phases of their growth cycle. It doesn't use it all there. Weather effects happen. But this allows so you don't have the logistics of sending a fertilizer truck to a remote field twice a year, as well as the loss because it's not an efficient use of all the nitrogen that's added. From an indoor agriculture or hydroponics perspective, plants pull nutrients from a hydroponic solution, and as they do that, the solution becomes basic over time, so the pH rises. You can add the nitrogen back in, which is acidic in nature, to help balance out and drive back down the pH. So that way the plant has the pH in a plant happy range, as well as the nitrogen can be used in uptake based on the plant growth cycle. For instance, again, the leafy greens prefer additional nitrogen at various growth stages. So you can also use it just as an added source of nitrogen. From the inedible biomass processing side of things, you can use a nitrogen plasma for biochar production, which can be used as filter style material. It can be mixed into the soil or whatever aggregate you have, or added into the water stream to provide nutrients back. Essentially, it's a plant nutrient recovery for reuse methodology. So once again, in remote locations where you have access controls to logistics restrictions, or if you have waste disposal restrictions, this might be a way to reuse some of your waste material at a cost of electrical power. So really the highlight there is indoor ag, hydroponic solutions for pH balancing and on-demand addition of nutrients. So kind of looking at a concept diagram of various ways plasma can support agriculture. You can have plasma treatment of seeds or the water that can be added to the seeds that can help emergence and growth. You have the plasma activated water aiding in plant growth. So this is the plant usable form of nitrogen being added as needed. Plant grows, you get edible produce. For us, you feed the produce to astronauts that are happy astronauts. Then you take the inedible biomass, you harvest it, you can process it in various ways. Earth, if you have time, you have composting. But if you want a quick turnaround on the order of minutes, you can use plasma. So that way you can take it. And this is where we most likely need development is nutrient separation or new solution rebalancing. Not every plant, if you harvest a tomato plant, reuse it and feed it to turnips or radishes, it may not want the same sort of nutrient balance for optimal growth. So there might be nutrient separation and solution rebalancing, whether you add more nitrogen in from plasma activated water or to help balance pH, or other additives, such as potassium hydroxide or something, to help the solution balance for reuse of the solution to try and close this crop cycle. That's something that we're looking at for long-term space sustainability, but it's still in its early stages. As you can see, a lot of this is lab scale, lab demonstration work. So there's engineering design required. Yeah, for a commercial industrial case, depending on which method you go, you'll need to scale both the plasma water and the biomass processing. The plasma water, I've shown, and we've shown with recent work, that we can make up to 17,000 parts per million of nitrate, which is very high, and then you just dilute it down with large volumes of water. And the biomass processing, of course, we did a small pop or soda can size reactor. So there's still some scaling there. We have ideas on how to scale this technology, but we haven't quite made it there yet. Our funding paths have taken us in a different direction currently. So a lot of this is just lab equipment with non-standard parts. And the importance of non-standard parts is that there's a lot of room for optimization. I'm a plasma physicist by nature, so we like when we get a power supply that we can change a bunch of settings. But from a commercialization standpoint, it is very inefficient the more knobs you add. So from the plasma water standpoint, we found what settings that it really likes in order to make nitrogen in a plant usable form. So we can make a higher power version that's a single discharge to scale it, or you can have a series of plasma discharges for smaller scale, lower power inline operations. So there's two variations I see of scaling that commercially, and that's kind of the same for the inedible biomass processing. Or you can look at the low power, always on version that might make 200 parts per million per day and 300 milliliters, but if you have it run every day 24/7, it'll eventually build up a concentration over time in a holding tank, or maybe your crop only needs a small amount of time for it. On the right-hand side is just a reference for a paper on some of the inedible biomass processing that we had. Currently, we have a provisional patent filed for the combination of these works, and we're open to discussion. I believe I'll hand it back to the tech transfer office to add some additional comments here. If I can exit this. Yeah. So otherwise, thank you, and I'll hand it off back to Lou, I believe.
Thank you, Kenneth. We've received some questions during the presentation, and we'll get to them shortly. But first, I'm going to give you a brief overview of NASA's technology transfer process. To access technologies like the plasma technologies for pH control and nutrient recycling that Dr. Engeling just described, you can search for them using NASA's technology transfer portal. All of NASA's patented technologies are listed in the portal at the website shown at the bottom of the slide. You can see NASA has quite a few patents available in a lot of different categories. When you go to the portal website and begin to scroll down, you'll come to the section shown here that allows you to search for technologies using keywords. Once you enter a keyword, you'll be taken to a new page that provides you with the results of your search. In this case, the keyword used was plasma, and the plasma processing of water and edible biomass for pH control and nutrient recycling technology showed up at the top of the search result. To see more information on the technology, you click on the Read More link below the technology. After clicking on the Read More link, you're taken to a new page that provides a description of the technology. This is only the top portion of the description, but the Ask a Question and Apply to License links at the top right of the page are important and will be mentioned again shortly. As you continue to scroll down the technology description page, at the bottom you'll see a Download Fact Sheet as a PDF link, which is highlighted here. Clicking on this will allow you to download the full fact sheet. This is what the downloaded PDF file for the fact sheet looks like. You'll see that it includes a description of the technology, its benefits, and applications for which it might apply. At the bottom of the second page, there is contact information for the NASA Agency Licensing Concierge. This person can help answer your initial questions and put you in touch with the appropriate licensing specialist at the NASA Center handling the technology if you'd like to speak with someone to get additional information about the technology and discuss potential licensing. If you click on the Ask a Question link during your search, you'll be taken to the page shown here, where you will fill in the information about yourself and your company and ask whatever questions you may have about the technology. This questionnaire will go directly to the NASA Agency Licensing Concierge, who will review your questions and get back to you with answers. This slide illustrates the NASA licensing process. Once you find a technology you're interested in on the portal, you can apply for a patent license through an online system called Atlas. A link to Atlas is provided in each technology description, as you saw in the previous slide, where the Apply to License link was shown. Once an application is submitted and accepted in Atlas, the terms of the license agreement can be worked out with the NASA licensing specialist, and the license will then be executed between NASA and the partner. All right, we've received some questions about the presentation, so thank you to everyone that has submitted so far. Feel free to continue submitting your questions by typing them into the chat box. If you have any questions for me about my licensing presentation, I can answer those as well. If we do not get to all the submitted questions today, then we will follow up with you by email afterwards. One question I see here is, what is the power consumption required for industrial scale application?
Right. So it really depends on the size. And please, the KSC team, please stop me if I need to be stopped. But from the earlier publication that should be out for you, search plasma, KSC, water, from a nitrate, we are around, back of the envelope calculations, we were around 2 to 3 times more expensive at that time than conventional methods. And that's without optimization, and that's without scaling of the technology. Since then, we've been able to improve our production of plant usable form of nitrogen, nitrate, and water by a factor of 10. So I believe to some degree it is scalable, but from an economic advantage standpoint, but we have yet to explore that on our end. We are looking at, supplying for a crew of 4 to 8 astronauts, whereas industry can be looking at, a hydroponic system to feed hundreds to thousands. So there is going to be some differences there, as well as we looked at pulsed discharges, alternating current discharges, and DC discharges. And there is room for optimization and scaling on our down selected plasma source that made it to the 17,000 parts per million. So the power consumption for industrial scale is dependent on how much you need, but the next question down on cost benefit analysis using the power consumption is that previously we were 2 to 3 times more expensive, but I think with our recent results, we would be comparable from a nitrogen standpoint. The inedible biomass pellet additive would still requires the development of nutrients separation and rebalancing. Lou, Jeff, do you want me to go ahead and just kind of pick questions and go from the chat here?
Yeah, Kenneth, if you can see them and you'd like to pick them, you sure can.
Yeah, absolutely. Greg Friedman at A Plasma. It's nice to see you here. Yeah, we can get you a copy of the presentation for sure. I know this plasma stuff's right up your alley, so I'm sure there's an in-depth conversation we can have at another point. Responding to Jeff's question to everybody in terms of scalability, how adaptable is a technology for various farming sizes, from small scale hydroponic setups to large commercial farms. It really depends on your needs. The nitrogen need of whatever crop you're producing, as well as the inedible biomass throughput processing for reuse. The nitrogen side of things, there is some interest out there. We have our technology, and I think our newest variation is not conventional thinking for the plasma field, just because we have to work in a space environment. So it forces us to look at things in different lights, so to speak. But you can scale our work in, as I mentioned earlier, you can have an array of plasma discharges, or you can scale up for a single discharge. But it really depends on the availability of your footprint, your power levels that you need to work with, as well as the required nitrogen content. So it's scalable, but we kind of need to know what you need in order to tell you what size it is, what size it's expected to be. From a safety considerations, what safety considerations have been addressed regarding the use of plasma treatment for water and biomass in agricultural applications, particularly concerning potential residues or byproducts? This is a good question. So our plasma jet in water, our first iteration, we ran into byproducts and stuff. Basically, you generate a plasma in water, you have that reactive environment, which can react with your environment. So certain metals didn't behave well. So we moved to a completely different setup that eliminated any residues in the water itself. From a potential byproducts, we don't strictly make a plant usable form of nitrogen. We make mainly nitric acid with which nitrate in the water. Um, we mainly make that with a very small amount of nitrite. And I believe the nitrite's within acceptable limits, but this is also with DI water, so ultra pure DI. Uh, our previous method we did explore with tap water, and we have results published on tap water as well. So this, water from a faucet. But our variation on the technology should eliminate most residues or byproducts. But of course, when you generate a plasma in an air environment, some of your byproducts are ozone, nitrous oxides. So you have to consider an enclosed environment or have some sort of filter in order to protect any potential leaks. There's still some room for improvement there. Power consumption for industrial, cost benefit, I answered both those. Lou, question for you. Is licensing provided to multiple companies on the same patent?
Actually, it is. NASA likes to use non-exclusive licenses wherever possible so that the technology provides the most benefits to the public. The more licensees we have that are producing commercial products using the technology, the more the public benefits. So our NASA's preference is for non-exclusive licenses. We do, however, occasionally entertain exclusive and partially exclusive licenses for certain fields of use or geographic areas, provided that there's justification for that because it closes off certain applications and areas for use to others. But so generally, the answer would be yes. We do license to multiple companies as much as possible on these technologies.
Okay, thank you, Lou. Next question down, when will this be commercialized to consumer products? So we've developed the technology to a certain degree, but we're looking at space environments, right? So from a consumer standpoint, our technology has a different end goal, and that's part of where this tech transfer program comes in. It's where you can work alongside our subject matter experts, the team here at Kennedy, our tech transfer office, to help commercialize this into a consumer product. I believe, Jeff, Lou, if you want to add anything to that.
Right. The commercialization occurs when a company licenses the patent and turns it into a service or a product that can be sold to the public so that the public benefits from the technology. So in order to commercialize it, we'll need to have licensees license the patent and actually further take the technology to the next step and make it available to the public.
Thank you, Lou. Next one down. What are the most important factors need to be considered in producing plasma water? From a cost standpoint is electrical consumption, right? So how energy efficient you are at making your product, what's your power draw, and the efficiency of wall power to plasma deposited power. And things that influence this are your electrode spacing, depending on your plasma type. If you have electrodes, or you can go to radio frequency and remove electrodes. So your conditions in order to make a plasma, so voltage, maybe frequencies in there, maybe pressures in there. So there's a huge array, but if I had to boil it down to three things, most important factors needed to be considered in producing plasma water is know how much you need to make from a uh, nitrate standpoint, because then you can choose your power supply, which will drive. We had a power supply that used 800 watts, and we had a power supply that used 100 watts. So really, it's your production rate, and then you can change your geometry from there. So unfortunately, there isn't really a straightforward answer other than what production rate do you need, and what in the time you need it. Do you need a lot in a short amount of time, or do you have days to make it? So then you can use a really low power over a long period of time, or an array of low power systems. Um, Brian, everyone, what is electrode material? So this is a good question. So for the jet setup, we started off right. It's nice if you can use everyday material, stainless steel, copper, tungsten. Doesn't work that well. You form tungsten oxide, copper oxide, rust. So actually on the other table, we have little vials where we had these things breaking off in your water, which is bad. Not only from a, you don't want this in your water, but it can be toxic to plants. So eventually we went to a platinum, right? You could use platinum, iridium, some exotic metal to coat it, but really our final variation of the system itself um, didn't have direct interaction with water. So we eliminated some of the rust and things going into the water itself. But I think unless you go to radio frequency plasma discharge, which is electrodeless, I would recommend an electrode material to be something that doesn't react with the list of species earlier in the chart. So mainly oxygen, nitrogen species. Um, Comment question from David Ashby. For space application, cost is not much of an issue, but what about the weight of the high voltage power supplies? They are usually monsters. They can be. It really depends on the power supply that you're trying to put forth. So we have high voltage power supply that weighs, I don't know, 5 to 10 pounds, and we have a power supply that weighs, you know, 40 pounds, or say 5 kilograms to 20 kilograms. But if you think about it, right, it's $8,000 to send up a kilogram to low Earth orbit, 80,000 to send to the moon. So if you send up one power supply and you can make it on demand as needed, then one power supply beats, sending up kilograms continuously of fertilizer solution. So in the long run, it works out, but it might have an upfront capital cost. Send one power supply, your point of return is year into it, whereas then you start saving money. So it really depends. From an industrial scale, though, your weight of your high voltage power supply will go up drastically. But if you're terrestrial, then it doesn't matter as much. For Brian, to everyone, how much wear is there on the electrodes? Kind of highlighted it when we had direct interaction with water. There was visible wear in 15 minutes. But I think you can tailor your plasma discharge parameters as well as your settings to mitigate wear, or switch to a less reactive material. DC dischargers get very hot and can be thermal, so you have thermal considerations wear. But if you go to a pulsed system, an AC, it's not as thermal, so you won't have thermal effects, but you'll still have the reactive species effects, so oxygen, nitrogen. Or if you go to radio frequency plasma, then you remove electrodes completely. But each system tailors your plasma chemistry, so you have different production rates based on your various power supply. And we highlight the different production rates in one of our publications, so you can kind of get an idea as power consumption versus production. From Ryan Robinson, has your plasma activated water been used for foliar treatments to prevent proliferation of microbial growth, powdery mildew, etc.? It has, actually. Because it's acidic in nature, it actually has good sanitization properties. Nitric acid, right? Low quantity levels of nitric acid. We didn't do it on powdery mildew, but we did it on microbial growth, Pseudomonas aeruginosa, E. coli, and I want to say Staphylococcus aureus, and with varying degrees of success. This is published. We have a review paper on the sanitization of seeds, kind of a plasma agriculture, space crop production. And as you well know from your question, you probably know that different strains of microorganisms are resistant, varying degrees of resistance. So it's not necessarily a one size fits all from a sanitization standpoint to prevent the proliferation, but we have seen success, at least mild success across the board. It can be 2-3 log reduction. Certain cases we ended up getting 5 log, 6 log reduction limits of the microorganisms on the surface. So it can be used for that aspect. So rinsing, cleaning of tubes, hydroponics, that could be a spin-off application of this plasma activated water, as long as your tubing is tolerant to the more acidic solution. I apologize if I say people's names wrong, by the way. John Kaiser, how are you accounting for potassium and phosphorus concentration differences between Hoagland and your system when comparing results? Biomass pellet likely has K and P, but is it comparable? This is a very good question. When we mixed the solutions, it was in the last 2 weeks of the project, so it's kind of the proof of concept. Can we do this? This is where the concept diagram I have, where you kind of go around, the nutrient rebalancing still needs there. So in future funded work, we wanted to study exactly what your question is. Look at the Hoaglands and the plant, the nutrient uptake in the Hoaglands, as well as what the Hoaglands provides, as well as nutrient analysis on our inedible biomass leached. We do have a paper that we published in a International Conference on Environmental Systems, so ICES, paper on the leaching part that might provide some insight, but I don't have the number off the top of my head. But we would need to do some sort of nutrient rebalancing long term. We might be able to get through 1, maybe 2 crop cycles, and you see degraded growth over time, but you'd have to rebalance at some point, because I'm sure some is lost in, say, the tomato itself that is edible. So next question down. Are there any other companies working on plasma activated water, or are you the only ones exploring this? There are other companies. Greg Friedman at AA Plasma might even have his own variation of this. But there is Nitricity is another company. I don't know. There's a couple more on beyond that. Some have started and failed, but it really depends on the need, the application. But electronics in the last few years have advanced enough, and the understanding of the plasma chemistry has advanced enough that, and unfortunately, the world we live in, prices of fertilizer have really increased. So now it's becoming more cost comparable or economic for these technologies. So there are other companies, but as I kind of alluded to earlier, even though I showed the plasma jet, we now make it in a different fashion that I think is much more amenable economically, than what the previous, or and what other companies are doing that I know of. So I would believe our version of it is novel in a sense that it's different than what's out there, but there are other companies if you look. Brian, did any researchers have any heart and lung problems working with the machine? So we work in a walk-in ventilation hood. So back to the safety aspects, if you generate a plasma in air, for instance, you'll make ozone, you'll make nitrous oxide, NO2, NO. So it's not something you want to breathe in, but as long as it's a controlled environment and you submerge it through the water, it will react with the water and be captured. Now some will come out as well, So you need some sort of filtering on the exhaust or things like that in order to prevent into the environment. The heart question, this is kind of an indirect thing. So plasma itself can introduce electromagnetic interference or EMI. So sometimes it is encouraged, especially if you scale these technologies, it might generate some EMI that may interact with pacemakers. So there are some published standards for EMI interference with pacemakers. So I would look at OSHA, things like that. So a commercialized system would have to be designed to either shield the EMI, which imagine, your microwave oven, right? You have a mesh screen over it that protects. So some engineering design considerations of a commercialized system would have to be taken into account to prevent EMI, not only from human heart, pacemaker, but also interaction with other systems. But none of us had any issues. But safety is very high on the list here at Kennedy Space Center. So anything we do is very thoroughly vetted from a safe standpoint. And if you want to have more in-depth conversation about safety things that we had to do, I'd be happy to have a conversation.
And Kenneth, I've got a few more good questions here. We'll run a few past you here.
Yeah.
How does the plasma treatment affect the microbiome of the soil or hydroponic system? And are there any potential implications for long-term soil health?
Yes. So this is kind of from the microbiome standpoint, I believe it kind of goes to from a sanitization standpoint, in hydroponics, you can use it to clean biofilm growth. If you get it acidic enough, it can really try and remove some of the microstructures. Hydroponics over time, as plants pull nutrients, become more basic, so you can bring the pH down. But from a soil standpoint, if you're adding acid to the soil in a sense, nitrates are acidic in nature, so eventually it drives the pH down a little bit. um, I'm not I don't want to a soil scientist, so I'm not really sure, because large scale commercial farming outdoor, right? After you harvest, you can till the soil and you take whatever inedible or whatever wasn't harvested and mix it back in into grades, right? And that probably helps balance the pH. But if you were to use the same soil consistently, without rebalancing some of the nutrients, eventually it would become acidic.
Okay, I have another one for you here. Are there any regulatory hurdles or challenges that need to be addressed for widespread adoption of this technology, particularly in the agricultural section?
Regulatory hurdles. From that standpoint, from a regulation, safety, the technology all is there to make it safe. Um, and your byproducts are well known. If you look in the literature, we have published information on it. I think all of that's fine. I think the biggest hurdle right now for widespread adoption has been the economics, right? If you can't save a dollar, it's more of a novelty as opposed to a must-have. But I think with recent price increases in fertilizer across the board, as well as the advancements in plasma physics and chemistry understanding that's driving down the cost of production, I think we are on the kind of the tipping point and edge, if not already past it, to where this now can be a more economic solution for application. Now, there's still some engineering that needs to be done. There's still some science. So there's some upfront costs, but I think it's on the verge of becoming economical. But regulatory, I don't believe so, because high voltage exists. The byproducts that might be made from these plasma applications exist in other chemical industries. So everything's already there. It just needs engineered into a complete package, and then a more extensive trade study on the economics needs to be done.
Speaking of economics, can you elaborate on the potential cost savings for farmers who adopt this technology, considering factors like reduced need for chemical fertilizers and simplified sanitation processes?
Yeah, so I alluded to it a little bit earlier. With our early published results, it was around, I would say, 2 to 3 times more expensive. than buying something. That may not take into the economies of scale, but we've been able to 10 times our production rate, but drastically reduce our consumable. So from that standpoint, we're becoming, it looks like we're more economical. I haven't ran the final numbers, but then you have the scalability question. And then scalability comes into logistics. Are you making it in a indoor ag hydroponic point of use, right? Say you're in the downtown middle of the city where it's expensive to truck fertilizer, or, the remote American Southwest where you have to send a logistics truck 80 miles out in the middle of nowhere twice a year, right? Then it becomes economical. But if your, fertilizer is down the street, then it still may not be. It really depends on, because it's now based upon electrical rates, utility rates, and each state has different, each state has their own different utility rates, provider systems. So if you have a low dose, low power system, you can use solar, right? So then it's economical because then it runs all the time. It's, renewable. I think a big aspect of it is it's more effective because you can make it on demand, point of use as needed, as opposed to flushing it. So if there's any sort of concern about runoff, agricultural runoff into rivers from over fertilizing, or yeah. So I think from economics, it's a case by case basis on whether it's more economical or not. But as the technology is more understood, more developed, it's becoming more and more economically favorable as the cost of traditional fertilizer methods are going up. Question popped up, can you elaborate on sustainability advantages? So the nice part is our methodology uses breathing air, so the air around us, and electrical power. You don't have a chemical-based process for it. So if you take your electrical power provided by solar, and then it powers your compressor and your equipment itself, then it's a renewable energy-based fertilizer system. Then it's, however you deliver it, right? As opposed to, I'm not as familiar with the standard traditional chemical process for making nitric acid and fertilizer. The inedible biomass processing, same thing. It could be powered with solar renewable energy. Of course, the cheapest way for inedible biomass processing is a giant composter, but that can take weeks to months, whereas this has a quick turnaround time. So as long as you can get your electrical energy from renewable resources, then it's a renewable way to process an inedible biomass or add nitrogen to your water, as well as, yeah, from a sustainability standpoint. That's kind of what my thoughts are. Any other questions?
I think I got one more for you, Kenneth. Here, hang on a second. Could you explain more about the potential environmental benefits of using plasma treatment for water and biomass compared to conventional chemical methods?
Yeah, that kind of goes along the sustainability and preventing agricultural runoff. Here in the United States, especially up in the Great Lakes region, the runoff can really promote algal blooms, the red tide, red algae, both in the freshwater lakes, and here down in Florida, we have algal blooms as well. So from an environmental impact, if you can make it as you need it from a point of use, you don't have your flooding of a field, or oversaturating and hope the plant takes up as much as possible, where even a 40% uptake, it still leaves a lot of runoff, agricultural runoff, which can have impacts on the local environment. And then from the other environmental impact, if you can get your renewable energy to power these systems, then you have it's electrical power and breathing air, as opposed to chemical processing. But yeah.
Okay, I think we've hit all the questions we've got for today, and we're pretty much out of time right now. So if we didn't get to any questions you might have during the Q&A session, we'll follow up with you by email if you contact us and let us know you have any questions.
Yeah.
Feel free to email them to us at the address shown here on the slide, and we'll be sure to follow up with your questions and answers answer those as well. We really appreciate you taking the time to be with us today, and thanks, Kenneth, for your time. Really appreciate it, sir.
Yeah, and thank you everybody for attending today. I recognize a few names, so it's good to see some familiar faces, and looking forward to hearing from anybody, and I'll help as best I can. Thanks to the tech transfer team for being here and putting this together. I appreciate it.
Thanks, everyone.
Take care.
Where are we off?